So today's video works more with indeterminate forms, which are the case where we use L'Hopital's rule. Some things that we already know. We know if we have a 0 over 0 or any combination of infinity over infinity, that is when L'Hopital's rule applies, where we take the derivative of the numerator on its own, derivative of the denominator on its own, and then reevaluate. And you keep doing that until you are able to then evaluate the limit. We also know that if we have 0 times some type of infinity, we can turn that into one of the functions over the reciprocal of the other function. That should then turn it into either an infinity over infinity of some sort. It might be a negative infinity in some there, or 0 over 0, which then makes it like what we just had above. And then if you have an infinity minus infinity, that is indeterminate because we don't know which one is getting bigger faster. So therefore, we can get a common denominator and get it as one fraction, and then it should give us a 0 over 0 or infinity over infinity type case. Now, some things that you don't have to use, that are not indeterminate at all, and that you don't have to use L'Hopital's as a result, if you have something going towards 0 and something that's then subtracted that's going towards infinity. Well, if you have a really small number minus something becoming enormous, well, that's got to go to negative infinity. If you have two positive infinities added together, well, it's a huge number plus a huge number has to be a huge number. Now, if you have just a single number like 7 or something or 4 over something that's going towards 0, it all depends on what's happening on the bottom. If the thing on the bottom is going towards 0, and going towards it from the positive side of 0 on both left-hand and right-hand limits, then it would go towards positive infinity, because your reciprocal of a really small positive number would be a really large positive number. If when you did the left-hand and right-hand limits of the denominator part, they came towards 0 from the negative side, then we would get negative infinity. However, if from one side it goes towards 0 from the positive, and one side it goes towards 0 from the negative, then we would not exist for our limit. So the new idea for this video is another indeterminate form, and it is when we have them in the form of a function raised to a function. If we get something approaching 0 raised to another thing approaching 0, that is an indeterminate form. We can't tell what is happening immediately. If we have some type of infinity raised to 0, or a 1 raised to an infinity, those are all considered indeterminate forms. To approach those, we will take a natural log of both sides. So if we take natural log of both sides, we can then swing the g of x out front to give us this, that natural log of y is equal to g of x times natural log of f of x. You will go ahead and you will evaluate this limit. Really what you'll be doing is finding the limit of the natural log of y. Because you're really finding the limit of the natural log of y, you will have to then get y by itself after you find your answer and do e raised to your answer. So because it will really be limit of the natural log of y equals some number, to find the actual limit of y, because this is really log base e of y equals your number, our actual answer will be e raised to that number. That'll tell us what the actual limit of y is. So when we're doing this, when we get our answer in the end, we will have to do e raised to it for our actual limit of the original problem. So we're going to look at this limit going towards 0 from the right. If we sub in 0 here, that'll give us sine of 0. 0 plus 1 is just 1. So we've got a 1 raised to something. Cotangent's graph, cotangent is cos over sine. Cos is 0 here. Cos is getting towards 1 this way. So cotangent will look kind of like that. So as we approach 0 from the right, cotangent's going towards positive infinity. So we have a 1 to the infinity case. That is one of our indeterminate forms, 1 to the infinity. So we will take the natural log. We'll think of this of y as y equals 1 plus sine 4x, all raised to the cotangent x. We'll take a natural log of both sides. And that will allow us to swing the cotangent x out front. So we're really going to find the limit now as x approaches 0 from the right of natural log y, which is this thing. And that's why in the end, when we get our answer, we'll actually have to do raise to it to figure out what our limit really of just y is. So we saw a second ago that cotangent went to infinity. The other one went to The other one went to 1, but it's now a natural log of 1. And as natural log goes towards 1, we will be getting close to 0. So we've got an infinity times 0 case. This is our 1 over. Well, cotangent is the same as 1 over tan. So we can rewrite this as the limit as x approaches 0 from the right of our natural log 1 plus sine 4x. And it's 1 over tan, which means just tan is going on the bottom. Well, the numerator is still going towards 0. Tangent's graph, tangent of 0 is 0. So this will be a 0 over 0 case, meaning we have to do L'Hopital's. So we'll have the limit as x approaches 0 from the right. Natural log's derivative is derivative of the inside over the inside. Derivative of 1 is 0. Sine 4x's derivative would be cos 4x times the derivative of the inside, which is 4, over your original 1 plus sine 4x. And tangent's derivative is just secant squared x. Well, if we sub in 0 now in our numerator, that'll be a cos of 0 really, which is 1. 1 times 4 is 4. And then on bottom, we'll have 1 plus sine of 0, which is just 1. So really, this part's just 4. Secant squared when secant's 0. Well, secant is really 1 over cos. Cos at 0 is 1. 1 over 1 squared is just 1. So we get 4 over 1, so just 4. But this is the limit of natural log of y. So we have now just found the limit as x approaches 0 from the right of natural log of y equals 4. We wanted to find the limit of y. So we've just got to convert to an exponential, so our answer is really e to the 4th. And that would get y alone. We'll do one more example of this type. This one is pretty clearly a 0 to the 0 case. That's one of our indeterminate forms. So we'll have y equal x to the x, and we'll take the natural log of both sides. Log laws allow us to swing that x out front. So we are now going to take the limit as x approaches 0 from the right of x times natural log of x. Well, this is going to be a 0 times negative infinity, because natural log's graph looks something like that. So as you go to 0 from the right, natural log is going towards negative infinity. This is our case where we've got have to write one of them as a 1 over. So we'll do limit as x approaches 0 from the right of natural log of x over 1 over x. And the reason you can do that is dividing by 1 over x is the same as multiplying by its reciprocal, which is just x. So it's really just the same problem. So we knew this on top was a negative infinity. On the bottom, as you go towards 0 from the right, that's going to make that a positive infinity because you're dividing by a really small positive number. Any type of infinity over infinity is an indeterminate form, which tells us to do L'Hopital's case. Derivative of a natural log is derivative of the inside over the inside. I'm going to go off to the side for the 1 over x. 1 over x can really be written as x to the negative 1, so its derivative is negative 1 x to the negative 2. Well, that can be written as negative 1 over x squared because negative exponents move to the bottom of the fraction. So this is really negative 1 over x squared. I'm not taking any derivatives or anything, but I'm just going to rewrite this differently. This could be 1 over x times the reciprocal. So times x squared over negative 1. And when you multiply those together, this is really the limit as x approaches 0 from the right. One side of x is out, and we just get negative x. Well, with negative x, as we go towards 0 from the right, that is just 0. So therefore, we know the limit as x approaches 0 from the right of natural log of y, natural log of our function, is 0. So we have to do e raised to that, so e to the 0, which in fact, that really is just 1. So our limit of x to the x, as we're approaching 0, is just 1. And we'll finish off the video with a couple quick examples similar to what we saw in the other video. Now this problem we saw in an earlier unit how to do it by factoring and find the limit, because you could factor out the top, cancel out an x minus 2. So we're just going to show you that you could also do it with L'Hopital's. Because if we went to sub in 2, we would get 4 minus 4, which is 0, 2 minus 2, which is 0. That is an indeterminate form, meaning we can do L'Hopital's rule. In doing L'Hopital's rule, we will now have the limit as x approaches 2, 2x over 1. Because you take the derivative of the top on its own, derivative of the bottom on its own. Well, when we do direct substitution now, this just gives us 4. Here's another example. We'll do some direct substitution. We'll have negative 2 squared plus 3 times negative 2 over negative 2 plus 2. Well, on top, oh, I forgot my 3, sorry. 3 times negative 2. So on top, we'll have 4 minus 6, which is just negative 2. On bottom, we'll have 0. Well, this is what I was talking about on the first slide. When you have a number over 0, we need to investigate a little bit further. We need to see if that bottom, if it is, when we look at the left-hand and right-hand limits of the bottom, are they both going towards positive infinity, both going towards negative infinity, or one of each? Well, let's investigate with the graph of x plus 2. X plus 2 looks something like this. As our x's approach negative 2 from the right, our y values are approaching from the positive side. But as our x's approach negative 2 from the left, our y values are approaching from the negative side. So because one's going from the positive and one's going from the negative, this is going to be a does not exist case, because the right hand and left hand will not be the same. If they had both been, say like we had an absolute value there, if we approach negative 2 from left and right, both those are approaching from the positive side, so therefore that would be an example of a case where the limit would exist and it would be infinity. But this one does not exist because that denominator there where we're going towards 0, one side's coming from the positive, one's coming from the negative, so our overall limit of this thing So overall right-hand limit is positive infinity. Overall left-hand limit, or I should say, overall right-hand limit is actually negative infinity because it's a negative over a positive. And our overall left-hand limit is positive infinity because it's a negative 2 over a negative. Next example, when we sub 0 in, we'll have e to the 0 minus 1 over 0. Well, that's 1 minus 1, which is 0 over 0. This is an indeterminate form. Therefore, we can use L'Hopital's rule, bringing us to the limit as x approaches 0. Any e's derivative is just itself, so e to the 2x times the derivative of the exponent, 2, over our derivative on the bottom, which is 1. If we now sub in, this will be e to the 0 times 2 over 1, so this then is just 2. And one last example for this video, if we sub in 0 here, we'll get sine of 0, which is 0, sine of 0, which is 0. 0 over 0 is an indeterminate form, so we may do L'Hopital's rule. We'll now have the limit as x approaches 0. Derivative of sine is cos, keeping the 6x inside the same, times the derivative of the inside, which is 6. On the bottom, derivative of sine is cos. Inside's the same, and you can write times 1 if you want, because that's the derivative of x. When we now evaluate, we'll get a cos of 0, which is 1 times 6 over 1, so therefore this is just 6. This concludes today's video. I'll see you in class next class period.